Hello, and a warm welcome to our webinar. Today goes out to our customers, students, power electronic engineers, and last but not least, to our competition. My name is Emilio Meza, and I'm your moderator for today's webinar titled Silicon Carbide in AC Motor Drives. Silicon carbide brings efficiency benefits to general motor drives, and changing market conditions mean that silicon carbide also makes economic sense. This webinar offers a detailed comparison of silicon and silicon carbide in both rectifier and inverter positions. Before we get started with the presentation, some words about our webinar platform. In case of any connection issues to the presentation stream or to the sound, please try to reconnect by refreshing the browser window. In your browser, on the right-hand side, you see the chat window, which you can actually hide to increase the screen space for the presentation. In case you have any questions about the content or technical difficulties, please let us know via the chat. All messages are private and only we can see them. We will try to answer your questions at the end of the presentation. The questions we do not manage to answer today will then be answered by email during the coming days. Also, you can send us an email to webinar@semikron-danfoss.com at any time, and we will get back to you as soon as we can. Lastly, we will share the presentation as a PDF at the end of the webinar. Your presenter today is Carsten Schreiter. Carsten received his degree in electrical engineering at HTW Berlin before joining Yaskawa in 2000. After a career in applications engineering, development, and product management in drives, Carsten joined Semikron, now Semikron Danfoss, in 2022. He is a product manager with a focus on the drives market, and he's now a product marketing manager. Enjoy the webinar. Carsten, the floor is yours.
Thanks, Emilio, and also from my side, welcome to everybody out there. Today we're going to talk about silicon carbide in motor drives, and I split the presentation in 5 sections here. So we will talk about why silicon carbide now makes sense in general to look at in motor drives. I will then show 2 examples that I've prepared. It's basically a comparison of silicon and silicon carbide in application. A quick look at products that we currently prepare for these markets, and we will close with a conclusion. So let's step right into it. Silicon carbide, it's basically not new. It's been around for a while, and it's being used in a couple of applications. Here I have, for instance, solar, energy conversion, energy storage, charging for electric vehicles, in the electric vehicles itself. But for several reasons, it hasn't been used in motor drives so far, or let's say the applications are very specific. It's a very small niche, not in the broad range. So why is that? Of course, cost has always been an issue. Then also lifetime considerations. Electrical drives or standard drives typically require some short circuit ruggedness, which was not necessarily given in former chip generations. Also, many people still think that silicon carbide only makes sense if you switch it really fast, meaning high carrier frequency and also very fast voltage rise times. Some of the things are like they are, but there are things also changing. And here are some reasons why I think that silicon carbide makes sense to consider right now. The first point I want to highlight here is efficiency. So there are more and more requirements for increasing the efficiency of electrical equipment in all industries that we see, also on all industries where motor drives are also used. Drivers are, of course, energy costs, which are continuously increasing, means wasting energy becomes more and more expensive, and saving energy makes more sense. So energy cost is a big driver here, but also the rising demand of electrical energy. So in our world now, we electrify much everything from cars to buses to home heaters, and everything is electric now, means more electric energy is required. But on the other hand, the grids and the generation cannot grow that fast. So we have to conserve some energy to fulfill the needs that are there. Talking about clean power grids, low harmonics, and all these kind of things. And here, silicon carbide actually can do really some nice things, as we will also see later. The application reliability. I briefly mentioned that in a standard motor drive, a mandatory requirement is to have it short circuit resistant. And with former chip generations, that was a bit of a problem. That has always been the Achilles heel of silicon carbide in motor drives. But with latest generations, we see some improvements here. So talking about 2 microseconds short circuit withstand time with the latest generations of chips. Of course, that's not as long as IGBTs can do, but it is at least something, and it's possible to handle with a very fast driver. So there is a way now also to have short circuit resistant drives with silicon carbide. And the last one here on this slide, there are more reasons. I just leave it with those 3, is cost. Silicon carbide has always been expensive, and it is still expensive, and it will also be expensive. So people who are expecting silicon carbide to be cost-wise at the level of silicon anywhere near, I think that will just not happen unless we have a major leap in production processes. But nevertheless, the costs are decreasing. That has several reasons. The wafer sizes get bigger, the chips get smaller with each generation, so we can make more chips from one wafer. That is decreasing the cost. But in general, as I said, we don't expect it to be anywhere near at the cost level of silicon. That's why it's very important when you look at silicon carbide, not just for motor drives, but here especially, it's very important. If you really want to make an assessment and find out if it's really more expensive, then it's not enough to look at the modules and compare module by module. You have to look at the whole system, and then it can make sense. And this is actually the main message that I want to send out with this presentation, and also prove with the application examples that you will see later. First of all, I want to quickly highlight the differences of silicon and silicon carbide. This is not bad to understand for the rest that follows later. So the first thing to point out here is are the on-state losses. On-state losses of a silicon carbide MOSFET are much lower than those of a IGBT, silicon IGBT. Why? You easily see if you look at this forward output characteristics here. Blue line is the forward output characteristics of a silicon carbide MOSFET, while the gray line shows the IGBT here. And you see that the MOSFET has the linear curve here, while the IGBT has this typical knee voltage here. And if you, for instance, look at the 10 amps line, then you see here that the MOSFET has a voltage drop of 0.5 volt, while the IGBT has a little more than 1 volt, means less than half of the voltage drop here, and that directly translates into lower on-state losses. And now you can imagine if you operate in partial load applications like fans, pumps, and these kind of things, then you're mostly in that area where you have lower on-state losses when you use a silicon carbide MOSFET. The second point, or the second thing to point out here, is the lower reverse recovery losses. In the silicon, when we use silicon carbide MOSFETs, then we typically use the embedded body diode as freewheeling diode for that time, and not an external or a parallel diode like in an IGBT. And this embedded body diode has much lower reverse recovery losses compared to standard pin diode. How much you see in the lower graph here. So you see there's, again, the blue line is a silicon carbide MOSFET. Here, this is mostly the characteristics of the diode. There's a factor of almost 20 in between. And that also contributes to the overall lower losses when using silicon carbide MOSFETs. Third point here, when we use silicon carbide MOSFETs, then we use the MOS channel for both directions, for reverse conduction and forward conduction. And that means, in the end, the delta T junction is lower in the MOSFET than in the IGBT, and that contributes to lifetime. We can switch the silicon carbide MOSFETs much faster than we can do with IGBTs. We don't have to. Some applications and drives don't allow that. We will come to that later, but we can if we want. And the last point here on this slide, silicon carbide has a better thermal conductivity, and that leads to very equal temperature distribution within the chip. There are no hot spots or anything like this, which is, again, a good point when we talk about lifetime. So what I did for this presentation, basically, I took, like you see here, active front-end drive, and this typically consists of two parts. We have the active front-end, the active in-feed converter, which is typically a 6-pack with IGBTs, so a controlled rectifier, switching frequency normally 5 to 6 kilohertz, and it always comes with large LCL filters to filter the harmonics. And most of the time, these are separate components, but there are also on the market some drives that have everything embedded. But it's a challenge to do this because, as I said, those filters are bulky and it's not so easy. So I looked at the active front-end part to see what happens if we use silicon or silicon carbide here. What is the impact on the module and also on the filter size? And I did a similar exercise for the inverter part. So here I also used standard 3-phase inverter. On standard inverters, we typically have some limitations. So the voltage rise time shouldn't be more than 5 kilowatt per microseconds, maximum 10, but this is already some special applications. So my calculations were done with 5. And also the carrier frequency is typically between 5 and 6 kilohertz is standard. Of course, you can go up to 15, but not more than this usually. All to avoid high leakage currents, EMC issues, losses on the cables, and these kind of things. So for both of these applications, I basically compare silicon and silicon carbide. For the one thing to mention, for the comparison or for the calculations, I used Semicell. Semicell is our free online available calculation tool for thermal simulation. So if you don't know it, it's a pretty handy tool, has pretty useful functions, many good functions. And well, if you want to use it, it's free on semikron-danfoss.com. You will find it there. Now let's have a look into the simulation results, starting with the line side. So active front ends typically look like I mentioned before. You have this LCL filter here and then the 6-pulse bridge. For my comparison, I used an IGBT7 or generation 7 IGBT module with 50 amps and compared that with the silicon carbide module, one of the latest generation, 32 milliohm, which is equal to roughly 40 amps rated or nominal current. The conditions I used for the simulations you see listed here: 750 volt DC, grid voltage 400 volt, 30 amps is my output current of the active in-feed converter, cosine phi, grid frequency 50 hertz. Then on the switching frequency, I set 5 kilohertz for the silicon because that's typically the standard in the market. And as I said, I wanted to find out what can silicon carbide do in this kind of application for me. So here I went up to 20 kilohertz. On the grid side, we're not so limited as on the motor side. So 20 kilohertz, I just used that as a ballpark number. There's probably, that can be tuned even, but it will be enough, you will see, to show the differences. RTH is the same, ambient temperature was the same. And here the results on the power module. So this column here shows the watt losses that we will see in that application on the silicon module with 5 kilohertz. In the right column, the watt losses that we will see on the silicon carbide module with 4 times of that carrier frequency, 20 kilohertz. I won't go to all the detailed values here, but important is to look at the total losses here. So in the silicon module, we have around about 250 watt here in that application, while in the silicon carbide module, we don't even have 200 watt, and that with 4 times the carrier frequency. So you see that we can save roughly or a little more than 20% of the losses here, which means you can reduce your cooling, you can reduce the airflow, you can maybe get rid of a fan if that fits. There's plenty of options that you have with these lower losses, or maybe even go higher with the carrier frequency if you want that. So plenty of options, design, freedom in design here. Now, I also had a look what if I go up with the carrier frequency up to 20, what happens with a line filter? I mentioned in the beginning, they're normally quite big and bulky and also heavy. And the result you see here. So this middle column is again the result with the silicon module and 5 kilohertz filter. And the right side here is the result for the silicon carbide module and the fitting LCL filter there. And again, I don't go through all the details here in the table, but important to see is this. So if I compare the volume of the inverter side filter, Li, it's, in the case of the silicon carbide module, 75% smaller. If I look at the grid side choke, that one is 47% smaller in my simulation here. And well, that is quite an achievement, I think. And of course, with a smaller volume, also the weight goes down. So we talk about 19.4 here versus 10 kilogram on the silicon carbide side. So we almost half the weight of this filter circuit there. Then also the losses go down. So while we have 463 watt on the silicon side, we have not even 300 on the silicon carbide side. So that's quite an improvement. And now you can imagine with this reduction in size and weight, it's, for instance, much easier to build, for instance, active front-end embedded motor drives. They become smaller. They are easier to handle, easier to put at the wall by the people who do the installation, everything that belongs to it. Also, the logistics have positive aspects here. Last point here is the cost of the filter. We use different material here, so even though the filter is smaller, it gets a little bit more expensive. But I must also say that this is just a rough calculation number. If it goes into volume, then probably that changes again. So to put it all together, silicon carbide in an active front-end converter can really, as you saw, bring us some benefits. We can increase the carrier frequency relatively easily. That helps reducing the audible noises. That also reduces the watt losses in the system. We can build smaller equipment, may it be active front and embedded drive, or even the separate components. It will be smaller anyway. Filter costs are comparable. Silicon carbide module costs are higher that I mentioned in the very beginning. But again, if you look at the total system here, the smaller system, all the benefits that you have along the supply chain, then I strongly believe that if you look at the total cost of ownership here, the silicon carbide side will win in this example. Very interesting, as I find. Now, let's look at the inverter side. That is also pretty interesting. That also shows pretty interesting results. So here I took a 35 amps module, also generation 7 IGBT, and compared that again with a 32 milliohm silicon carbide MOSFET, also one of the latest generations. As I mentioned, the DVDT, the voltage rise time, I did not change. I adjusted for both simulations the gate resistance so that the rise time is roughly 5 kilowatt per microsecond. And also the carrier frequency I left at 5 kilohertz for both. So in a sense, we really break down break the silicon carbide. It's like a race car with handbrakes pulled, but you will see it still makes sense. The application, I choose a pump. Why? Because it's pretty easy to calculate the current and different load points. A pump has typically, or in a pump application, the speed and the torque, and with the torque also the current, they are related with the square root function here. So there's the actual one, the blue one, that's a bit more difficult to calculate. So I just use the theoretical curve here, the red one, for calculating some load points. And at those load points, then I compare silicon and silicon carbide. As a motor, I choose a standard P permanent magnet motor with 15 kilowatts, 26 amps, 50 hertz, so something that you can buy off the shelf, and that is also used in such kind of applications. My drive parameters are 560 volt, 5 kilohertz switching frequency, DVDT 5 kilowatt per microsecond, ambient temperature 40 degree, and overload like we have it in pumps, typically 110% for a minute. Now let's have a look at the result. So here, what you see, I go directly into the graph. What you see here, the gray line, the gray solid line, shows the watt losses of the silicon module. The red solid line shows the watt losses on the silicon carbide module. And you can already see that over the whole operation speed, and if you remember the load curve, one slide before or two slides before, The speed is related to the current here. So with lower speed, we have lower current. And over the whole speed range or current range, we have way lower losses with the silicon carbide MOSFET module here. So if we assume our pump is running in that speed area, 40 to 80%, I think that's quite a range where most of the pumps are running most of the time in their life, then we talk about 62 to 54% lower losses. If we look at the efficiency, that's these are this is represented by the dotted lines. Gray again is the IGBT module. Red is the silicon carbide module. You also see here there's a huge gap in between, while the IGBT module does not even cross then 99% efficiency. The silicon carbide module is here close to 99.5 and all the way down above 99. So we have an improvement here of 1.7 up to 0.8% in efficiency. And that's quite an achievement. Now, this is at the module, but the drives have more losses than just module losses. So I wanted to see what happens if I put such a module into a drive. And here I choose a standard drive that you can buy off the shelf. Again, for these drives, you can quite easily calculate the losses and the load points that I selected before online. There's a calculator that is related to the ERP regulation, so manufacturers have to push that out. I used that to calculate the drive losses in my load points, and then I subtracted the IGBT losses and put the silicon carbide losses on again. So the step that I did before is now applied to a drive. And what comes out, you see first in the upper chart, at the rated load of my pump, the losses in the drive would go down almost a quarter, 24%. And that's quite an achievement with just changing to silicon carbide. And if you look along the load, so from 40 to 100%, we also see here that the losses are way lower. So we talk about still 11 to 24% lower losses. And also in the efficiency, there's a gain of 0.5 up to 1% for the drive. And again, this is something that is quite impressive, I think. Now we talked about, or I briefly talked about cost, and I said that cost of silicon carbide is of course higher than that of an IGBT module. And I also said that return on invest has to be looked at. So you have to look at the system and at the time to see that it can pay back. And that's actually what I did here. So my assumption is that if somebody buys a drive 15 kilowatt silicon or silicon carbide, then the adder for the silicon carbide drive would probably be something about 90 to 100 euro. That's a pretty conservative guess. In reality, it's probably even less. Depends also on the volume, of course. But so what I then did, I created an average load profile. So I say that 10% of the time the drive is not running at all, the pump, right? Pump application. 5% of the time it's running at 40% load, 17% of the time it would be running at 50% load, and so forth. So I created this load profile here, and with that, I calculated the annual watt losses in kilowatt hours for the IGBT module, or the drive with IGBTs. And what comes out is this, a bit more than 600 and roughly 650 kilowatt hours. And if I do the same with silicon carbide, then I'm here around 300 kilowatt hours. So I have roughly 55% lower losses in 1 year. So if I take these 354 kilowatt hour savings and I can put them in CO2, 172 kilogram less. That's good for your footprint. But I can also turn it back into money. So for that, I use these energy costs. Now you will laugh at me and say, hey, I paid this last time in 2021. That's correct. Now it's much higher, but it's also going down again. Anyway, if I do the calculation with these low energy cost here, then I would save in a year 92 euro. If you that compare to the price adder here, it's obvious that the added price of the drive comes back within a year. So now the drives typically are not designed for 1 year operation time, rather for 10 or 15. That means from you pay, and then after 1 year, the drive basically earns money or saves money, or however you want to put it. And I believe if you do this kind of way of looking at an application, then in quite many applications you will find that with silicon carbide you can create such a benefit. Then, as next step, I had a look at the power density. So for this exercise in the upper part here, I basically used again the same modules as before. So this 35 amps IGBT module and the 32 milliohm silicon carbide module. And I put the same load on them. And then I tried to run them at the same junction temperature. So this, for instance, 130 degree for the same load condition needs this kind of a heat sink. If I do the same exercise with silicon carbide and shrink the heat sink so that the silicon carbide module also gets up to 130 degree junction temperature, then it comes out that the heat sink that I need for that can be 66% smaller than for the IGBT solution in this particular application and with a selection of modules here. And this also quite opens some possibilities. So you see easily that the heatsink is smaller, so you need less airflow. Less airflow means maybe a fan less, or you can go down with the fan speed. Less airflow also means that there is less contamination in your drive on the panel by dust or whatever is used, whatever is in the cooling air there. It's more silent. For some applications, the fans are also, the fan noise can also be disturbing. It's easier to create drives with higher degree of or higher IP ratings, so protection against dust and humidity. And also, if you can build smaller drives, then of course the box for the drive will be smaller, so you can put more boxes on one pallet. In the end, you get more drives on one truck. So also you have you can have less space in your warehouse. So if you look along the supply chain, also there, some benefits can be created. So it's an endless chain that you can basically follow on and on and on with benefits created by silicon carbide or by the application of silicon carbide. In the lower example, I turn it around and I said, okay, if I can do this, then I could probably also squeeze out more power of the silicon carbide module. So I did the same thing here. This is the IGBT running at 130 degree junction temperature. And then I increased the load on my silicon carbide module to see at which load I would reach the same junction temperature with the same heatsink also. And it came out that I can apply almost 20%, 19% more power to the silicon carbide MOSFET. And also that gives you some possibilities. If you think how standard drives nowadays are built or framed, typically what we see is we have one mechanical frame, and in that one mechanical frame, manufacturers put 2, maximum 3 electrical frames. So there's one size, and in that size you will find a 5.5 and a 7.5 kilowatt, and the next one is then the next mechanical frame. With silicon carbide, you might have the option to even add one more electrical frame in that mechanical frame. Of course, providing that the terminals and all that kind of stuff around can lead the current, but you can, by that, you can reduce the number of frames in your drive lineup, and that reduces not only the number of parts that you need, but also the design effort, the testing effort, certification effort, and all these kind of things. Again, you see, if you look at it from a system or from a holistic viewpoint, then it totally makes sense to consider silicon carbide. And if you just look at module by module, it will not make sense. So it's really important to understand these kind of things. Another thing you can do, I don't have a simulation done for this, but also play with the carrier frequency. Higher carrier frequency can easier be done in silicon carbide than in IGBTs. And what it helps with is to reduce the losses in the motor windings, for instance. So higher carrier frequency usually means your current waveform and voltage waveform is a bit better, and that reduces the losses on the motor. You can then build more compact motors or increase the lifetime of the motors, or it's also easier to create drives to run turbo applications where we talk about 1,000, 2,000, 3,000 hertz output frequency, some things like this. It's a niche, of course, but it's there and it has to be served somehow. So also here silicon carbide can bring in some good benefits. Higher carrier frequency also means there's less audible noise from the motor. So in any application where people are close to the application, close to the motors, they will like you if you can increase the carrier frequency from 5 to 10 or to 15 kilohertz easily. So that is also very easy with the Carbide here. And also, if you, for instance, use output filters for sine wave filters in some applications, for instance, if you use higher carrier frequency, it should be possible to make those filters much smaller and maybe embed them in the drive or have less panel space. Also here, if you apply properly, silicon carbide can provide some benefits. The products, it's actually only one slide. What you see here is the Semitop E1, E2. That's our equivalent to the Easy packages, market standard package. And what we are preparing here, which is ready to be sampled, are packages in CIB configuration, pretty standard in drives, and also 6-packs and with 36 milliohm and 18 milliohm. It's based on the latest Gen 4 SiC trench technology from Rome. And these chips actually provide some short circuit capability. I mentioned that in the beginning, 2 microseconds is what we see here at 150-degree junction temperature and 800 volt DC voltage. If you go down with those values, so lower junction temperature or lower DC voltage, then the 2 microseconds even get a bit longer. Again, it's not super long, but it's at least a value that is possible to handle in some way by a fast driver. These packages that you see here, they will be pin compatible to standard CIB and 6-packs with IGBT. So it means if you want to use them and play in an existing drive, then you can put them in the same PCB, adjust the drivers a little, and can learn to work with silicon carbide here. The Semitop E, also compared to some market standard modules in the same range, has way lower RTH, 20%. It helps a bit on the cooling design, and we provide those modules with pre-applied thermal interface material, either with high-performance heat paste or also with phase change material, which gives you then some good benefits when you process the modules in the production of your drives. If you want to know more about it, you can scan later when you have the PDF, this QR code, to see a video where we speak about those things. We come to the conclusion. So if we want to put it in one sentence, or if I shall put it in one sentence, then I always say silicon carbide actually provides new degrees of freedom in design. And that is illustrated by that picture here at the right. When the IGBT is that small triangle here, then the silicon carbide would open you this large triangle area in whatever dimension. So if you want to optimize the space of your drives, of your construction, silicon carbide can help it, as we could see, to a great extent. If you want to go for higher power, silicon carbide can help. Higher power meaning in the same thermal design, right? If you go for higher efficiency, silicon carbide is the way. So it really opens some new possibilities that, or does away with some limitations that we have if we stick with IGBTs. We also saw that even at low switching speed, it can totally make sense to use silicon carbide, and you can achieve impressive results with it. We see that it's a perfect fit for variable torque applications. Remember that pump application, which is always most of the time running in the partial load range, where the current is rather low, and then the benefit of the MOSFET having this lower forward voltage plays out. It really is the key to create more efficient drives, and which then also contribute to decarbonization and carbon footprint reduction in factories and productions. We have it in proven packages, so there's nothing new. If you use easy packages or Semitop E1, E2, then you know what it is. We just put those chips in there. You can just go with the current design, swap the module, and play around. And most important, if you look at it correctly, meaning from a system perspective, then it can really give you good advantages, and it can be even cheaper than IGBT solutions are today. But again, it is really important to have that holistic view and not compare module by module. That is the main message here. If you now think, okay, that sounds all good, and I want to start playing with silicon carbide, then of course he should contact us, and here's why. So we, Semikron Danfoss, we are the largest chip-independent module manufacturer in the world, and I put emphasis on this chip independent because that gives us the option to, on one hand, deal with many partners or selected partners on a long-term base, and also to select the right chips for the right application, as we do here for the motor drive. So that's good for supply security and also for having the proper chip in the right application. We're not just doing that since yesterday. We have 25 years experience in packaging IGBTs from third parties, but we're also already more than 15 years packing silicon carbide into our power module, so we know how to do it. We have all the standard packages at hand, as you saw before. So that was semi-top E. Of course, we have all the other standard packages too, and we could also put some silicon carbide in there if that is desired. We have the technology that allows us to also drag the full potential from the chips. Talking about soldering, but also sintering. We're pretty good in sintering, different bonding technologies, different substrates. We know how to handle these kind of things. I mentioned supply security is given because with all the suppliers and also the silicon carbide suppliers, we have long-term agreements. We also have early access when chips are developed, so we can work on with there and tune them in one or the other direction. And last but not least, we have a great application engineering team with great knowledge, and those people can really help you when you want to implement silicon carbide, but also other modules into your applications. With that, I'm at the end of the presentation. I hope you gained some good insight in what silicon carbide can do in motor drives and in your application. And if there's any question, then let us know now.
Thank you very much for the great presentation, Carsten. And to the audience, I have just shared the presentation. You can navigate down to the 3 dots where it says Apps and click on Handouts if you want to download that PDF. We have received a few questions that we can discuss. Also, we might not get to all of these, and some of these are customer specific, so we probably won't discuss those. But I'll go ahead and start here with the voltage ratings. So with silicon carbide, what are the voltage ratings? What's the highest voltage ratings that we have for these devices?
At the minute, what we have at the minute is 1,200 volt devices. That's also what you could see on this slide here, where I had the module. So these are for it's not even written. Sorry for that, but those are for 1,200 volt.
Okay, and I'll say on slide number 11, there's a couple questions. It's having to do with the magnetics.
Yes.
So I know that you're not necessarily an expert, but maybe
That
you can
is
answer
true,
a couple
yeah.
of these. Yeah. So the first question being, why are the core losses in the silicon carbide module smaller than the silicon module?
As Emilio said, I'm not an expert for magnetics. I did this exercise together with a supplier, but for this, I can say that we use different material. You see, this is GO, and this is megaflux, so it's a different material that probably also leads to lower losses in the core. The other thing, it's also the geometry is a little bit different here. It's not the same core. That might also relate to it. But if you want to dig into the details here, then you can come back to us afterwards, and I can find that out together with the guys that helped me with creating especially this part of the simulation or the comparison.
Mm-hmm. And I'll say another question about this was relating to the cost and why the cost difference, but I imagine that's about the same.
I briefly mentioned there's different materials used. So this megaflux seems to be a bit more expensive or way more expensive than the GO. So I even thought we have a smaller choke here. It's in the end more expensive. There might also be different materials in the winding, so aluminum and copper. I can't recall all of it, but that's main of the reasons. Again, that's the same offer, like I just mentioned. If you want to have details, just come back to me, and I'll find those things out and discuss with the people who helped me with that comparison here.
And so here's another question. It's about overload conditions.
Yes.
I think I don't know, this is necessarily silicon carbide, but can you offer some insight on how the converters are rated and whether it's maybe 110% of the motor rating, or how does the converter compare to the motor rating for the overload?
A converter compared to the motor rating.
Yeah. So if a motor has, given horsepower rating, does the converter need to have a given overload factor,
Well,
110%?
normally how we choose the drives is by the motor current. So if there is for my example here, for instance, I have this motor current of 26 amps. Then typically an 11 kilowatt drive that you find on the market has a current of roughly 24 amps. It's too small. That would be 11 kilowatt. A 15 kilowatt typically has 31 amps. It's a bit too large, but you have to choose it. Otherwise, you can't run the application, and that's how it would typically be done. And then for the overload, of course, you take 100% of this, make sure your drive can do it, and that's it. I'm not sure if that was the question, but
I think that's good enough for the time being. Yeah, it wasn't such an exact question, but let's see. Are there any commercial products that are using silicon carbide at this point in motor drives?
You're talking about drives?
Yes.
Well, there are, but of course I can't name the
you know,
companies.
that's what I'm saying. No naming companies or anything like that. But I think
there certainly are. It's only a very few. I mentioned that in the beginning. It's not. It has not arrived yet in the motor drives market, especially not in the standard drives market. If we go to so in the standard drives, it's very rare at the minute, but I believe it will be changing in the next years. Sooner, not soon. It will change. If we look at specific applications in the HVAC sector, for instance, we'll see it much faster. That's what I can say. Again, I can't name anyone here. Of course, I know few, but
I have the mute button ready. I'll start clicking and start saying names.
Beep, beep.
So here's a question about lifetime for silicon carbide.
Yes.
How does that compare with silicon?
That's a very good question. So in general, if we pack it the same as an IGBT, then and run it with the same delta T at the junction, then the lifetime is shorter. That's what it is. But in the end, you have to again look at the application. One of the reasons why I choose the pump here is also it doesn't have a lot of overload, so we won't see a big jump in the delta T junction here. It's a pretty straightforward application. If you have an application like, for instance, a crane or a lift, where you start with high carrier frequency, very high load at very low speed, and you always have these big jumps in the junction temperature, then it's probably worth to think about twice and see if silicon carbide is the right selection or not. In any case, you have to run a thermal simulation, and with that thermal simulation, we can go into our lifetime model and calculate the power cycle that comes out with that condition, and we can tune it in one or the other direction. So you can't get there without doing this thermal and lifetime calculation, and then select the right module for the right application.
Right.
There's no general answer. You have to look into the details.
Very specific, yeah. And here's one I already know the answer to, but I'll go ahead and ask. Does Semikron Danfoss have a standard line of drivers to go with silicon carbide?
We don't have a standard line of drivers. We have some drivers that might be tunable for playing around with it, but we don't have standard drivers at the minute for driving those silicon carbide modules.
Okay. And then one question here, I'll call this the last one. I know there's a few that I'm not getting to, but we reached 45 minutes already. When you were reaching the 5 kilovolts per microsecond, did you only change the gate resistors, or did you do anything with the gate capacitance or anything like that?
For the simulation, just the resistors. That is all I can adjust. The model in the simulation, of course, considers the gate capacities and all these kind of things, but I can only adjust it with the resistor.
Okay.
And again, this is again the thing. If you have your application, you build it up, then you have to start measuring and go into the details and tune it there. But for simulation purpose, only the gate resistance.
All right. And I'll say the other questions, we have your email addresses and we will email this out. So Carsten, thank you very much again for the presentation. It was great. To the audience, thank you for joining the webinar. I hope you enjoyed it and you could take away some useful information. If you have any further questions, please contact us at webinar@semikron-danfoss.com. Thank you again and have a great day. Bye-bye.